Okay, today's class will continue with and complete VCO once and for all. Okay. So last week we were looking at the VCO tuning, right? So maybe we went a little bit fast. So let's go through it quickly again. So you want to choose a KVCO which is pretty small, in the tens of megahertz range. Okay, normally, because if you have large KVCO, you will have larger AM to PM noise conversion. Okay, and if you have any coupling inside the PLL, that will cause purse. Okay, then you are going to split your total capacitance into a fixed capacitance and a variable capacitance. The fixed capacitance is going to be used for discrete tuning. The variable capacitance is going to consist of your varactor. Okay, so once you do this, so you have your varactor which gives you analog tuning and the fixed capacitance which gives you digital tuning, and so you will get a bunch of frequency versus control voltage curves. And you will need to make sure that there is enough overlap between successive discrete tuning steps. Okay. The other thing you have to remember is, obviously, as you go from lower frequencies to higher frequencies, your KVCO will change. Obviously. Okay. In one case you have larger capacitance, other case you have lesser fixed capacitance. Okay. So definitely your KVCO will vary. Okay, because you're going to have different number of fixed capacitance on and off. So what you're going to do is you're going to make sure that is you try to restrict it to within what your PLL can withstand. Okay. Okay. So now if you look at your discrete tuning, this is a continuous tuning. So far we have seen single-ended implementations. You can also do something like this for the discrete tuning. Okay. So if this is C, you make it something like this. And of course, if your transistor layout, for example, is the source drain is not symmetric, then you may need to do something like this. Okay, you need to have half the transistor switch the other way. Okay, sometimes that can happen from layout, if you depending on the number of fingers and so on. Okay. Okay, then you have some parasitic capacitance on this guy. Okay, you're going to have two kinds of parasitic capacitances. One is your CGD. In this case, okay, let's assume it's CGD. Okay, it's your overlap capacitance. Okay, the other one is going to be so in this case, so let's yeah, that doesn't matter, CDB. You have your drain bulk capacitance. Okay, so what happens is your Cmax, sorry, yeah, I know it's CGS and CGD, but since the transistor is in triode, it's symmetric. Okay, so that shouldn't be a problem. And for this transistor, it will be CGS and CDB. Okay, don't worry about that. So what is your Cmax? Cmax is just C when your switch is on each side. Okay. What is your Cmin? C in series with okay, you have C here, you have CGD and CDB in parallel. Okay, so this is approximately CGD plus CDB. Okay, because you're assuming that CGD and CDB are much smaller than C. So now this discrete tuning also has a certain Cmax by Cmin, and you want to maximize this just like you did for a varactor. Okay, that will also maximize your tuning range. Okay, so if you take your CGD and CDB, they are going to be proportional to width. So as your width increases, your CDB and CGD are going to increase. However, the Q is also going to be proportional to the width. Why? Now your series switch has a series resistance, on resistance. Okay, so when it's on, you're going to have a C in series with an effective resistance of the switch. that resistance decreases as your width increases. So your Q is going to be proportional to W. So this is the basic trade-off you're going to have when you design your discrete tuning. So you need to choose W carefully such that you trade off your Cmax over Cmin and your Q, which means phase noise and tuning range effectively at the end of the day. Okay, phase noise depends on Q, tuning range depends on C par. Okay. So the other thing you need to know is varactor rebiasing. So if you remember, some of the varactors we looked at had curves which look like this, something like this. Okay. So the tuning range you get is in this range. What you actually want from your circuit is probably like this. Okay, because the control voltage, so the control voltage is being produced by some kind of circuit which has only 0 and VDD. Okay, so you can't afford to have negative voltages. Okay, so you're basically losing that much of tuning. So if you want to make it up, you'll just have to rebias your varactor, no other go. So let's say this is your varactor, this is your VCOP and VCON. Okay, you'll have to do something like this. So you're going to effectively rebias the varactor such that it comes here. VB may not be negative, will not be negative. So what you'll have to do is, what you're interested in is this guy. Okay, so your VB can still be positive and shift this curve. Okay, because what this delta V is across the varactor only. You're talking about this guy, this one, this to varactor. This comes from VC. It's always between 0 to VDD. Okay, think about it. You can do it. Take it from me. You can do it. Okay. So you may have to do something like this. Okay. You may also be able to do differential tuning. Okay. For example, actually I don't need this much. So let's say one capacitance does this. Okay. You may have a different capacitance which does this. Okay. And of course that is definitely possible, because whether you take an NMOS or a PMOS varactor, you will have different curves. Okay. So what you can do is you can exploit this to get a wider linear range for your control voltage. So what you can do is, this can be VC1, C1, and VC1 minus VC2. Okay. So in which case your if you plot your frequency versus delta VC, earlier you only got this much, now you can get some extra tuning on the lower end. Okay. The biggest problem with this, the two slopes at any point will not be constant, because you are using two totally different devices. Matching the KVCOs will become a problem. Okay, getting a very linear KVCO would become a problem. Okay. Rather, what I should say is, Okay, you could.
One of the C1 is right.
Yes, yes. So let's say C1 and C2. Okay. So one of them is constant in the range, approximately constant in the range where this thing shows extra tuning. Okay. Oh, actually, I should shift this. You're right. It's a good point. Okay. So you may want to something like this. You will need a shifted curve. You're right. Okay.
What is the point in putting control voltage and then fixed capacitance?
And a fixed capacitance?
C2 is like fixed capacitance.
Sorry. That's also a varactor. Okay. One is C1, other is C2. Okay. So one problem is you could either have nonlinear KVCO or you could have different slopes. For example, in one side you could have one slope, other side you could have a different slope. Okay, that matching becomes a problem. Okay. Why is it an issue? So what will happen is, if you are okay, so the slope changes here, right? If your frequency is okay, obviously this is not 0 for the frequency, but if frequency is caught there, the tuning you will get will not be all from C1, all from C2. Okay, so you're basically, when you're tuning around this range, you'll get different KVCOs on. So if the PLL is stuck there, right, and if something is, let's say, temperature is causing, you will see different variations on positive and negative sides. Okay, that's one thing. Second thing to remember is that these are all linear curves. Remember that the actual signal is actually a very large signal here. Okay, so the actual curve you are looking at is the average voltage here versus the average voltage here. And obviously if you are moving along two different slopes, you will definitely get some weird behavior. Okay. Okay, so finally we will just devote a quick page to the DPLL, okay, the digital PLL. Basic idea is, so instead of having, your normal PLL consists of PFD, charge pump, loop filter and so on. So what you are doing is converting an input phase difference into a pulse width, and then that pulse width into a current with a variable pulse. So effectively into charge, which is going into a loop filter. Loop filter filters out high frequency components. You feed a DC voltage to the VCO. Okay. In the case of the DPLL, you want to make completely digital blocks. Okay. So it looks like this. So you have what is called a time to digital converter. Okay. It so happens that that is just happens to be a string of inverters and some certain flip flops. Okay. So what you are doing is you are basically converting the delta phi here. Oh, sorry. Delta phi here into a digital word. Okay. Which carries the phase and frequency information. Okay. Then you're going to use some kind of filtering, digital filtering, to filter out the digital word. Then that is directly fed to what is called the DCO, or the digitally controlled oscillator. How do you implement this? It's actually fairly simple. So all you have to do is so let's say it looks like this. You're just going to have a bunch of capacitor banks. Okay, and the resolution of this capacitor bank is going to be low enough such that you can effectively tune in frequency. Okay, so if you see what kind of resolution you need, so let's take some typical values for L and C. So let's say L is 0.5 nanohenry and C is 4.5 picofarads. F naught is 3.6 gigahertz. Okay, so let's say you want a resolution of let's say a couple of kilohertz at this frequency. Okay, delta C will turn out to be approximately 5 attofarads, which is 5e minus 18. Okay, and believe me, these kind of resolution capacitances are possible. Okay, in the latest processes, this kind of capacitance is definitely possible. So what people generally do is they try to rely on fringing capacitance. Remember that fringing capacitance, these parasitic capacitances are usually very low. You try to keep them low. So if you want that kind of people create the capacitances using fringing capacitance. Metal to metal capacitance, exactly. Okay.
Turning on that switch parasitic.
Of course, so you'll have the same exactly. So your switches need to be extremely, so you may not be able to do it in the latest process, the older processes. But if you look at like 65 nanometer or 45 nanometer, you'll probably be able to do it. Okay. So people have implemented these. Okay, and they work pretty well. So what you're effectively going to do is your digital word is going to vary instead of your control voltage varying to compensate for, let's say, temperature variations or voltage variations or whatever. Your digital word is going to vary, okay, because this senses the change in frequency due to that. The main motivation to do this is two things. One, if you make it completely digital, the assumption is you can make it very predictable. That is the idea. Okay, so in other words, earlier your loop filter R, C, all those things vary over process if you implement on-chip loop filters. If you have an off-chip loop filter, it's obviously bulky. You need to, reserve a pad to go out. You need to worry about the inductance going out into that. Lot of issues. So, having a completely on-chip digital would make things very nice because the bandwidth of that filter will be very fixed, right? Over process temperature doesn't matter because they're just numbers at the end of the day. Okay, that is the main motivation. Now, these kind of PLLs work very well when you have to do something special with the PLL. Okay, normal PLLs, yeah, there is some RC variation, but you can try to compensate for it. You can design the PLL such that you take care of some amount of RC variation, definitely. But there may be cases where you want it to be very fixed. For example, if you're doing some kind of, so there are ways to do what is called phase modulation through the PLL, where your input being instead of an FREF, okay. So some, let's say, you're trying to give some phase modulation along with your FREF, and you can also give it inside this guy also. Okay, so it will have the same. So what will happen is, if you give, let us say this is around DC, okay, this is some low frequency variation that gets transferred to around F0. Okay, anything which is slow enough will not be filtered out by the loop filter in analog or the digital case. Okay, and that will end up at the control voltage, which means the VCO phase and frequency will change slowly, and at the output you can get a very nice modulated waveform. Okay, that is polar. It's quite often used in polar modulation or phase modulation. Okay, in those cases, you obviously want your filter at this point. You want your signal to completely come through, your phase signal, which means the bandwidth of the PLL should be very predictable. Okay, shouldn't vary that much.
Will there be phase noise?
Will there be phase noise in? Absolutely, of course. You will have noise from this guy. You will have noise from this. This is still an analog circuit. Remember, you are still trying to resolve analog quantities. You'll have quantization noise from this guy.
So even TDC will also get modulation.
Even what?
TDC will also.
Yeah. Even TDC will have quant noise because the output is digital. Absolutely, right? So you'll have quantization noise. Of course, your DC is still an analog circuit. Divider is still an analog circuit. So you'll have normal phase noise from those circuits. Okay. Yes, these I have not shown the switches, but they're obviously turned on and off.
That is also like
So the input is digital, but the output noise, phase noise, is not quantization noise. It's actually an analog, right, frequency signal.
So that means frequency to which you have to log is between getting.
Okay, so I have shown a very simplistic view. What you will typically have is some kind of delta sigma, inside, which will dither very well between these caps. Okay, so that you will have a very, you can do noise shaping. Okay, some amount of shaping such that your average is exactly at the frequency where you want to set it to. Okay. Okay. Now, couple of other things about the VCO. I mean, obviously, all the techniques we have talked about are common to both DCOs and VCOs. Okay, because as far as the VCO goes, we didn't talk about anything specific to the VCO alone. You can use the same things for the DCO. Okay, except for the fact that tuning, you're doing it in a different way. You do the same things. The way you choose the inductor, capacitor, currents, everything is the same. Okay. So I think that yes.
What kind of noise does this quantization cause in the shape of that noise?
It will actually cause your N-band noise floor to go up.
No, that is thermal kind of noise. Or
It will be like thermal kind of noise, right? Yeah. It will be a flat white noise.
it is comparable to other analog service.
Yes.
The one by.
Yes. You will still get the same 1 over F noise, everything from your VCO. Okay. So all those things will not change. Okay.
So if I have input is digital, output is also digital.
Yes.
So where is the quantization?
Where is the?
Quantization.
So depending on, so you want a certain accuracy on your capacitance control, right? If you start truncating your, see, there is only a certain limit on the size of on the length of the digital word you can put in. Okay. Exactly. And similarly, what will happen is, as you keep increasing this guy, there will be implications for the TDC also, because that will need to be wider and wider. It will need to resolve finer and finer phase resolutions, that is time steps. Okay, so time differences. So primarily you are right. The quantization noise will be limited by the TDC rather than the FIR filter. Okay, but there will be some from both. You need to do eventually. You need to do some amount of truncation. Okay, because you won't be able to handle that amount of that length. The typical word lengths you will see here will be like probably greater than 15-20 bits easily. Sorry, output of the TDC going out, and similarly the phase information coming in, both those things. So now obviously the phase information I have shown here as an analog quantity. You can have that going in. So this is going to have some kind of sigma delta in here, the divider. We have not talked about the PLL, but it's going to have some kind of sigma delta which controls the frequency. So along with that fixed frequency, you are also going to send in the frequency control, the phase information. Okay. What about? Okay, that's a very good question. So one of the problems with this kind of PLL is the fact that you have a bunch of digital circuitry which is switching right at the control node. So you will have problems with spurs at the output of the VCO, definitely. Okay, what you can do is you can try to do some kind of dithering, because now you have a lot of control over the digital word. You can try to do dithering, okay, to see if it helps with the spurs. But typically what you'll see is, okay, all of these things are going to be clocked, okay, typically at the reference frequency. And so definitely at the reference frequency, you are definitely going to get very large spurs. Okay, there's no doubt about that. Okay. Couple of other techniques which you can, of course, you are welcome to use in your project. One of them is, so this is first of all very popular, and there are many versions. Okay, we'll just look at one of them. Let's do it this way. Okay. So this is one example of a tail current filter. So first of all, why do you have CB? CB is there because if you have a very large CB, what happens is, so remember that your current source noise, right, gets mixed down to your frequency of oscillation, 2f0. So let's say there could be current source noise at 2f0, which gets down converted to f0 through mixing action. Okay. So this CB is large enough such that it's a very low impedance at 2 omega naught. So your ion tries to flow through the capacitor rather than through the circuit. So that is one thing you can do. The other thing which is commonly done is, sorry, this should be LT. Okay. Again, you can make sure your LT and CT have a parallel resonance at 2f0. Why? Remember that the noise from the devices, remember that you have folding down of noise from higher harmonics, right? So if you add a series, if you add a parallel resonance circuit in series with the VCO, which is high impedance at 2f0, what happens is you cannot have 2f0 current flowing through the tank, flowing through the tank and the VCO effectively. Okay, so which means any noise, so that if you have noise at 2f0 from the devices, you cannot have a noise current flowing and folding down to create noise at f0 plus delta omega. Is that clear? Okay. So the drawback of this is that you do need a second inductor. So you are going to use some significant amount of area.
But it only after the second harmonic, the higher harmonics.
Yes, but remember when we discussed the gamma function, which is the ISF, the Fourier series coefficients, right? They actually go down for any typical, for any real oscillator. As you keep increasing the harmonic number, right? The noise which folds down from the harmonic number keeps going down. Okay, and you will see it when you design your VCO. You need to make sure that you choose a large enough number of harmonics, and same thing with the mixer also, by the way. Okay, your when you do the what is it called, steady state analysis, you will need to choose a number of harmonics that you that the circuit is going to, that the simulator is going to consider for the circuit. Okay, so what you have to do is you will have to choose. So if you keep increasing the harmonic number, what you will see is the noise will keep increasing little by little. Eventually it will settle down to some value, and that is the number you should be using for all future simulations. Okay, same thing for the VCO. Okay. Yes. Here. At the drains of the, of which? Here. Where? Here. Okay. Okay. Yes, but you are going to have noise from, okay, so the noise from those current sources are going to come in, right? At the end of the day, remember, okay, so first of all, the current sources are not ideal. Okay, so they have some, so if some other circuit tries to inject, they will have some impedance. So the minute you put in current sources, you have to worry about headrooms, you'll have to worry about noise from those current sources, you have to worry about a lot of things. Okay, so that thing will not help, because if you have an ideal current source, it won't allow the current to change. But if this thing is trying to inject some noise, definitely normal current sources will have some compliance, right? So they'll definitely allow some of the noise to slip through. Okay. Yes?
But our output also will be create current source.
Sure, of course. Yeah, output is always swinging. So, another circuit which is commonly used along with VCOs is your voltage regulator. Okay, you can have something like this. Okay, you can have something like this to change the voltage. So typically the supply will be noisy. It's going to come from some kind of switching circuit, DC to DC converter. Okay, so this will be quite noisy. You want to protect your VCO. So if you look at all the circuits we have looked at so far, the VCO would be the number one circuit you would want to try to protect, because you want to create as pure a signal coming out of that as possible. Okay, so you can pretty much talk of it as being the most important block in any transceiver. Okay, of course that's one of the reasons why you are spending some extra classes on the VCO itself. Okay, so what you want here is something which is attenuated by a certain amount. So you can add a regulator. Sorry. Okay. So if you plot the PSRR for this guy, you will get some certain. Okay, so what you do is you can also add a cap here. Okay, let's say a cap C0. What happens is, so you have a certain regulator loop, right? So at very low frequencies you will get very good PSRR, and obviously your op amp is going to have some finite bandwidth, so your loop is going to have some finite bandwidth, so your PSRR is going to start increasing. At higher frequencies, your capacitance is going to give very good PSRR, because any disturbances are going to be stabilized out by the capacitance. Okay, so your PSRR will start going down again. So let's say you might get a PSRR of maybe minus 50 dB or something. Okay. Now if you use a PMOS transistor here, you will get better PSRR. Okay, but the bandwidth will also be lower. First of all, you have to worry about compensating the loop. Okay, this is actually a source follower, whereas the other one would be a common source. Okay, so you get much better gain out of that, so you'll get better PSRR, but you'll have to start worrying about compensation.
This is all common mode noise that is getting detected.
Yes.
Translation is.
Remember, even if you have common mode noise, we talked last week about, if you have, remember we talked about AM noise, right? Through the varactor, you will always have AM to PM conversion. Okay, so that will end up as phase noise. Okay.
Sir, are we interested only at omega naught or the PSRR number at omega naught?
No, you are interested in PSRR. See, remember, if you have a, okay, I don't think I went through it last week, but it's there in the notes. If you have a very small frequency FM here, okay, you can find out what component of it goes through here, through the certain, let's say you didn't have the PSRR, so you'd have some component of it go through here, and remember, okay, so if I redraw this capacitor, okay, so if you have a very slow moving wave here, so this is constant, this is varying. So effectively your control voltage is going to be varying at a very slow rate, and that ends up, so this was your VCO, you will get spurs at, okay, you will get spurs at F0 plus or minus Fm, and of course you will actually also get harmonics, it so turns out. Okay, so you definitely have to worry about this. Okay, so obviously the things you have to worry about here, regulator noise is definitely going to be important. Okay. So obviously if you're going to design the VCO, you can't farm out the regulator design to somebody else. You'll have to do it yourself. So you'll end up having having to do both the regulator design and the VCO design by yourself, because there are a lot of things interacting. You have to worry about the headroom, you have to worry about the noise, okay, you have to worry about so many things. Okay. How about VCO buffers? So depending on the load, you have many different kinds of buffers. So you can have just a single stage, okay, you can have a single stage but with 3 of them in parallel, okay. Okay, obviously if you start, let's say you need to, okay, take the simple case of a PLL, okay, the VCO will need to drive the signal path, which is your mixers, as well as the feedback divider, okay, and you definitely don't want interaction between the feedback divider and your mixer, so you will most probably have to separate out these dividers, okay, so you'll definitely have at least 2, maybe more. So now if you start stacking up more and more buffers, you'll have to worry about capacitive loading of these buffers, okay. So what happens is your tuning range will get reduced. In fact, you'll have to recenter your frequency, tuning range will get reduced. So what can you do about that? So of course the easiest way to do is now do 3 stages. Okay, you can have a 2-stage buffering. So this will definitely help with that. So your C in here is reduced. Obviously what you're trading off is power consumption. The minute you put in a second stage, you'll have to worry about more power consumption. The other thing this 2-stage buffer helps you with is kickback noise, okay. So the circuit where, okay, so the circuit which this is driving could be a divider, actually it will typically be a divider, okay, or it could be kind of mixer, okay. Definitely the divider is going to be switching, okay, it's a switching digital circuit in most cases. So now you have to worry about kickback affecting your VCO. So obviously if you have a 2-stage buffer, it helps more, your reverse isolation is better. Okay, so what kind of buffers would you use? The most commonly used ones are just simple pseudo differential form inverters, okay, each side has a separate inverter. Obviously you have to worry about matching between these two. You want to make sure that your zero crossing information does not change. Your delays have to be matched and so on, okay. Okay, we are going to come to that, okay. Yes, you are right. Remember that buffer typically limits your noise floor. We talked about that last class. If you just consider just the tank alone, the VCO alone, if you see whether you take 1 over f noise or thermal noise being injected into the tank, it always gives you either 1 over f cubed or 1 over f squared, okay. So eventually you will hit a noise floor which is limited by your buffers, okay, because otherwise you will always keep getting 1 over f squared, okay. So you can do this. The only thing you have to worry about with inverters, they are actually very low noise, okay, definitely there's no doubt about it. Inverter noise, the in-band noise, especially the 1 over flicker noise area, will be much lower than the VCO, okay, will be 20-30 dB lower, you don't have to worry about it. But obviously thermal noise will start mattering. Okay, now the last thing you have to worry about is for the inverter, if you look at, let's say if you take one switching instant, obviously the inverter itself is going to contribute maximum noise in this window while it's switching, okay, and obviously any noise which is injected by the devices or externally is going to change the switching instant, right. So that is what is going to affect your phase noise. So what can you do? So you want to decrease delta T. So the only way to do it is larger inverters will switch faster. Okay, but obviously this means more power. Okay, so you have to remember that. Sorry? Of course, more parasitics as well. So typically you deal with parasitics by increasing the number of stages. Okay, so if you have too much capacitance, yes, definitely. So there is definitely an optimum number of stages, optimum power, and so on. So you'll have to figure that out for any design. If you're given that you have to drive a certain capacitance, you'll have to figure that out by yourself. Okay. Right. So this is just your noise floor. And why does this buffer noise matter? Why do you care about noise very far away? We talked about, when we talked about phase noise, we talked about, when the phase noise is very large, and when you have in-band noise, that could desense your receiver either from a nearby transmitter or from an interferer. But we never talked about why your far out noise matters. Okay. So if you consider duplex systems where you are transmitting and receiving at the same time, okay. A simple example is WCDMA, okay. Actually we don't need this. So on the frequency axis, if you look at your bands, they look like this. So your TX, you're going to have your RX band, which is usually the RX band is a little bit higher than the TX band in most of these cellular systems. Okay, and the spacing depends on the particular band you're working with. Okay, so they have a particular band class. So they have different band classes. So that gives you different spectrum. Okay, different sets of spectrum you work with. So if you're going to transmit somewhere here, okay, so this is going to have some noise. So it looks like this, and now you are trying to receive something which is very small here. Okay, so automatically that's where you will get hit in terms of sensitivity. And this will be pretty large. Okay, your TX to RX spacing is typically in tens of megahertz in most cellular systems. Okay, so remember, so 1 hour of noise will typically go to till a few hundreds of kilohertz. Okay, and sometimes less, by the way. Actually 1 over f cube, let's call it 1 over f cube. Okay, will be okay. So your 1 over f squared could be few tens, maybe 10, maybe 20, something like that. So maybe from 1 megahertz to maybe 20 or 30 megahertz, and beyond that will be your flat noise. Okay. Okay. So finally, let's end the VCO topic. Okay. Actually, before that, sorry, I think I forgot one more thing. If you have buffers instead of inverters, you could do a tuned load. Okay, a tuned amplifier. You could either instead of doing a tuned, you could also do something like this. Okay. So this is a big fat inductor. Okay, so it's going to be large enough such that effectively it is going to be like a DC current source. Okay, inductors don't allow current to change suddenly, okay, and if you make it large enough, at the frequency of operation it's going to look like a high impedance, okay, and so your input can be VB plus Vn, and so if you look at your signal current, it flows like this, okay. This is called the open drain configuration.
If that inductor is very large, so the parasitic capacitance, the inside impedance will also not be.
You mean here? Oh yeah, definitely. You have to worry about that. So which is why if you're designing for if you're designing for, let's say, a certain frequency or for an on-chip implementation, then there is a limit on the sizes. I mean, obviously, larger and larger inductor it would seem like that would be better, but definitely you're going to have parasitics associated with the inductor, and that is going to steal away some of your signal. So you do have to worry about it, definitely. Okay, typical thing, the inductor would be anywhere from a few, let's say 7 or 8 nanohenries to all the way up to 15 or 16 nanohenries, maybe a little bit larger. Okay. Okay. I think you all probably know about this effect of division on phase noise. So if it goes through a divider, okay, a frequency divider, okay. So let's say at this point, it looked like this. Okay, it's going to look like this because your frequency phase relationship is linear. So if your frequency is divided by n, phase is also going to get divided by n. Okay, so the noise in the phase, the magnitude of that is going to go as 1 over n. And if you remember, I think either last class or the class before that, we found that if there is a certain way to go from here to the side bands. So this is just the magnitude. You take this, you can expand this, so you have cos of a plus b, so you'll get a term which is at cos omega naught t, that will give you your fundamental oscillator. Okay, this is your oscillation frequency. Okay, and through your you can expand out, you'll have a term which has cos of phi n and sine of phi n. Okay, so what you'll do is you're going to expand it as a term which is omega naught plus, okay, so let's say this corresponds to let's consider a small sliver of frequency delta omega of this phi n that will contribute to phase noise at omega naught plus or minus delta omega. Okay, so you have to go through some Bessel functions and so on. We won't worry about it in this class, but you can assume that delta omega is much smaller than omega naught and you can do this. Okay. So what that means is this power goes as 1 over n squared. Okay, so which means if you divide by 2, you'll get a 6 dB reduction in phase noise at the same offset. Doesn't matter.
If it is a resistor, we can consider it as
Okay.
It's like taking only every end.
Yes, sure. Well, if you look at most dividers, they don't exactly work that way, right? So typically they're counters. Okay, so you have to worry about noise on every edge. Going to, you don't just discard like n edges. So that is what you're talking about is like pulse swallowing, right? So these dividers will not be like that. They'll be synchronous counters. Okay, so you have to worry about noise from every edge. Okay. Yes, it will be a square wave. It could be a square wave, it may not be a square wave. If you implement a digital divider, like let's say CMOS divider, it will be a square wave. You could have, for example, tuned dividers. They do have tuned dividers, analog like CML kind of dividers, which need not necessarily have full scale amplitude. But it doesn't matter because you can model the divider as a case where you have some frequency division, and then you have some amplification. So your noise will also get automatically amplified with it. The change in amplitude will not matter too much for your phase noise itself. Okay.
So the divider itself will have noise.
Yes, divider itself will have noise. So you have to, actually we have not even considered that. Normally the divider noise will be much lower, okay, and the 1 over f regions and your 1 over f squared regions. The divider on the other hand will give noise at the flat noise region, definitely. Okay. Okay. So let's quickly, in 2 minutes, we'll go through the VCO design steps. Most of it is what we have already talked about before. Okay. Okay, maximize tank Q, which is RP. Maximize the output swing, which is V naught. But don't saturate. You want to operate in the region between current limited and voltage limited. Do you remember that from last class? Have enough startup gain, okay, at least 2 to 3x of what your calculation gives you. Like for example, for the cross coupled oscillator, we got GMRP greater than 2. Try to use like GMRP greater than maybe 4 or 6, okay. You want to maximize tuning range? Start off with minimum lengths for your transistors, okay, for your cross coupled transistors. Later if you do see noise, coming from them, then you have to see what you can do to, let's say you might have 1 over f noise, so you might need to increase the length a little bit, but you need to worry about that later. For starting off, this is good because they are going to switch faster. If you use them, they are going to have better FT, which means you can reduce your current in the device. So we know these two things. So from 1 and 2, you want to maximize you want to maximize 1 and 2 at the same time. You want to maximize L and Q at the same time. So in other words, choose the largest L, which will give you the largest Q. Okay. And of course, topology. So you have lots of them, right? Okay, you have Colpitts. We discussed these in class. You actually have others, Hartley. Okay, you have you have hybrids between the two. You have hybrids between the cross coupled and the Colpitts. Okay, so there are a lot of options. So the topology choice matters. So depending on whether you're interested in phase noise, tuning range, minimizing the number of inductors, depending on that you would choose one of these. Okay, normally your trade-off will be among these for most applications. Okay, you would have to choose between NMOS, PMOS and complementary. Okay. Okay, we'll stop here. So from next class we'll continue with wideband amplifiers. Okay, we're pretty much done with LNAs, mixers, VCOs. So most of the basic building blocks of your transceiver. The power amplifier, I'm still not sure. I'll probably cover it in maybe 1 or 2 classes. It's kind of a very complex topic to cover in one course. So I thought we'll do something on widebanding. Okay, there are applications where you need, instead of narrowband amplifiers, which we have been looking at so far, you want to widen your bandwidth. So we'll look at that starting from next class. Okay.